opposite or an electric motor backwards. So I showed you this electric motor. I didn't show you this one. I showed you a video. And so I brought one to show you. Let me pull it up here. See if you can see this. This is electric motor. This is a magnet case, or these are just some permanent magnets. And then this is the armature. This is the thing that spins here. And it has a couple of batteries that are just connected to that armature. Let's see if I can show you. You can see that there are wires that run from the battery. You connect these little loops right here to this copper wire. And then it puts a current through this armature, which is this just coil of copper wire. Remember that the armature, you can see part of it is stripped right here. It doesn't have any insulation on it. And then if you flip it over, actually over on this side, it's stripped there. And then if you flip it over, it has insulation on there. I'm not sure if you can see that very well. Let me show you. So right now I have a current that is going through this copper coil. And if I spin it, it should keep going. It's really hard to get the armature perfectly balanced. Yeah, that's pretty good, actually. So that's how an electric motor works. Notice if I pull this off, it'll stop. You have to give it a little initial pump. But remember, as it's moving through this magnetic field, or when I have this current on this magnetic field, it creates a torque on that loop. And as it spins around, it's that torque that causes it to spin around. Also remember that each time it spins around, that current is moving in the opposite direction. Like when the coil flips over, the current is moving in the opposite direction like we showed last time. And that causes the forces to switch, which would cause it to go flip-flop like we talked about last time. But because of the way we do the insulation on the armature on this wire, it turns the current off every half turn. You want to see it again? Yeah, I think it's pretty cool actually. These are, the lady in the video made it look very easy, but they're actually pretty difficult to make. Just to get them balanced properly is difficult. But this one goes pretty well. All right. I also wanted to show you something else. This is a little hand crank generator. You can pick these up for pretty cheap online. So it's just a little thing that you spin, and then you can put some wires on it. I'll pass this around. Oh no, I won't. You can put some little lights on it. You see them. It's how the generator works as well. You just have an electric motor or a gasoline-powered motor. It spins a coil of wire in a magnetic field, which is all you're doing here is you're just spinning a coil of wire, and then that causes an electric current to flow through the lights. But if you don't believe me, and a generator is really just the same as a motor. So I can connect these two. So I connect one end of the generator to the other end. And so now when I spin this one, it's going to cause a current to go through the wires into this other generator. So what do you think is going to happen? All right, so notice I'm generating a current with this one, and it's turning this little generator basically into a motor. So a generator really is just a motor, except instead of using a current to produce motion, it uses motion to produce. Also notice that I'm spinning this one pretty fast, but because I get some off the circuit, this one spins a little slower. So there's not a perfect one. Okay? All right. And I want to show you one other thing, and I will pass this around because this is kind of cool. This is a two-stroke motor. You can, except I've cut it away so you can see the piston and stuff, and it's all pretty cool. So I'll pass it around. See, there's the piston right there. I'll pass it around. You can look at it. But the main thing I wanted to show you is on this little flywheel. Where are they? Right here. Here and here, you have two little magnets. And then these magnets interact with a piece of metal, which is right here, and it generates a current. Because what I have is a changing magnetic field. As this thing spins around, I get this changing magnetic field from these magnets interacting with this metal coil, and it sends a current to the spark plug. So this is the basic idea of how your electrical, the ignition, or the, what's it called? The spark system. I don't know what it's called. You might know what it's called? Yeah, no, not combustion, but spark plug. Like the distributor in your car. I think it's different now. But anyway, this is how we generate the electricity that creates the spark. So I'll send this around. You can take a look at it. Just notice the magnets here, and you can feel them actually as it spins around. Because you'll just sort of feel a little pressure as it spins around. So again, this changing magnetic field actually generates an electric current. All right, let's do some questions. Turn this off. And again, I'm not going to go through all these notes, but we are going to, let me just sort of go over and summarize our three ways that we're using the right-hand rule. Should have a blank page somewhere. Where is it? I'm just going to use this space right here. You can, wherever you want to put it, but I just want to, you should have this in your notes, but I just want to summarize and just make sure that we're all on board with how we're using the right-hand rule, because we have three applications of the right-hand rule. We have the QVB application, the ILB application. This is for the force on a charge. This is the force on a current-carrying wire. These are basically the same. Remember, I let my fingers go in the direction of the first vector. That would be either V or I. They fold towards the second vector. That would be B in both cases. And then your thumb gives the direction of the third vector. That would be the force. So for example, if I have a positive particle moving in this direction with a velocity, say in a magnetic field that is into the page, then this one would feel a force that would be up. And there are a variety of variations on this, and we've done some in class, and we'll do some more today in our concept test. But the force here would be up. And then you can apply similar things with the idea of a charge moving through a wire. Now, another one which you saw on the screencast, hopefully, was the magnetic field produced by a wire, by a current-carrying wire. The B field of a current-carrying wire. And this is a slightly different application of the right-hand rule. I have a wire that has a current through it. I let my thumb go in the direction of the current, and then my fingers wrap around to give the direction of the magnetic field. So if I imagine, say, for example, this is a wire, and there's a current coming towards you, then I'll let my finger go in the direction of the current, and then my magnetic field will go around in this direction. Faraday discovered this back in the late 1800s or so, but he found that the magnetic field, if you put a compass all around, that the magnetic field changed direction. Is he okay? So my magnetic field goes around. You can use your right-hand rule to figure that out. Use your thumb, and it'll show the direction of the magnetic field. All right, we'll come to that. We'll see that in the concept test, but you should have already seen that. But those are three applications of the right-hand rule. Well, let's do some practice problems. Let's see. We'll pick up those that we left in the book. Make sure you go back through here. If you didn't watch those videos, then please do, and make sure that you're up on these things. Okay, here we go. This is using the cyclotron equation, which is the idea behind a mass spectrometer. you have a magnetic field, particle at a certain velocity, and I give you the radius of its path. I want you to tell me which of these unknown particles is it. Now what you're going to be doing is determining what is the mass to charge ratio, which you can do with that cyclotron equation, and then select the particle based on that mass to charge ratio. All right, let's do about 10 more seconds, okay? About 150, let's stop. Just 5 seconds. Just if you're not sure. 150. Awesome. Oh, looking good, actually. All right, so A is right. On this, you want to start with our cyclotron equation. And remember that our cyclotron equation is based on this idea that the force on my charged particle, QVB, is equal to mv squared over r. That is our centripetal force. It is a centripetal force because that force is always perpendicular to the motion. It's always pulling it in a circular path. And then I can solve this for r, and I get r equals mv over qb. That is my cyclotron equation. That's on your equation sheet. And it just comes about from that idea that the magnetic force is a centripetal force, and it will always cause your object to move in a circular path. And so now I solve this for the mass to charge ratio. M over Q is going to be RB over V. R, I'm told, is 0.052. B is 0.4. And V is 2 million. 2 times 10 to the 6 meters per second. And I get 1 times 10 to the minus 8. And then if I look at these particles and I ask myself what are the mass to charge ratios for each of these particles, that's going to be this one. The mass to charge ratio is 1.67 times 10 to the minus 27 divided by 1.6 times 10 to the minus 19. That is the mass to charge ratio, and that's how we determine that this unknown particle is a hydrogen particle. Very common way to determine unknown materials because it allows you to measure their mass to charge ratio. If you know their mass to charge ratio, then you can determine, or at least eliminate, what the particle is not. Most likely just figure out what it is. Okay. Let's do some of the concept stuff in your back part of your book. How far did we get along in here? I know. How did you know? How far did we get? 5.4. We didn't do that. We did not do it? Okay. So let's look here. Here I have two particles that enter. They both have the same mass and the same speed, and they follow these two paths. And I want to know which of these particles has the bigger charge. Particle A or particle B have the bigger charge. Again, these are the paths that they follow, and then these are the detectors where they detect the two particles, particle A and particle B. going to stop at 55. 55. Okay, B is right, I think. Let me see. So my equation, cyclotron equation is mv over qb. I have a bigger radius for particle A, and that means I'm going to have a smaller charge. So particle A has the smaller charge, so particle B, is that what we put, B? Yeah, so particle B has the bigger charge. The one with the smaller radius has a bigger charge. Or another way to think about it, actually, if Q is big, that means R is small. So bigger charges are going to have smaller radii for their path. What is the sign for these charges? Is it A positive or B negative? A positive or B negative? Remember, just use your right-hand rule. If the force comes out opposite what you think it should be, then it's a negative particle. All right, I'm going to help you out. I have a velocity vector that's in this direction, it's going up, and then the magnetic field is into the page, so I let my fingers hold into the page, and so the force should be in this direction if this were a positive particle. Now, is the force that's causing this circular path, is it initially in this direction towards the center of the circle? That's the question I want to ask. If it is, then it's a positive particle. If it's not, if the force should be in the opposite direction, it's a negative particle. All right? That didn't help you very much, huh? Let me repeat what I said. So what you want to do is use your right-hand rule and ask yourself the direction. Well, first let's ask ourselves the direction. What should the direction of the force be? The force that's causing this particle to move in a path that looks like this, should that force be to the left or should it be to the right? That's the question. To the left or right? It should be to the left, right? The centripetal force that causes circular motion is always towards the center of the circle. So my force here is going to be in this direction. My velocity should be in that direction. So let my fingers go in the direction of B. They have to fold towards the magnetic field like this. And so the force then is to the left, as it should be. So that means that this particle is what? A positive or a negative particle? It's a positive particle. So this force, or this charge rather, should be a positive particle. So A is the right answer. I'm going to stop at 208. Sorry, no joke for you. Guys, I know that it's hard being out on Friday. I know that screencasts aren't terribly engaging. I'm sorry for that. It's just still going to be on this Friday. I'm not going to give you screencasts to watch. I know that. Do y'all like watching them? No, you didn't at all. But I'm not going to give you those to watch. We'll just sort of have a clear day. But it was really hard to miss 2 days of class, and I just don't like doing that. So I'm sorry. That's what it is. But okay. So same idea here. Can't really see the figure very well. It doesn't matter though. You should be able to see it in your book. But what happens to the kinetic energy of the proton? As this proton enters this magnetic field and it goes in the circular path, what happens to the kinetic energy of that proton? Does the kinetic energy increase, decrease, stay the same, or does it depend on the directions? All right, I'm going to stop at 45. 45. You are awesome. Because a centripetal force does nothing to the energy, right? Because in order for the centripetal force to increase, or in order for a force to increase the energy of something, the force and the displacement have to be in the same direction. And that's not true for a centripetal force. It's always perpendicular to the motion. So that force does no work. Oh, awesome. Remember tell y'all, it's like y'all like the best class I've ever had. Did I tell you this? Have I told you that? I have. All right. That's awesome. Where's my heart? Okay. It does stay the same because it's a centripetal force. It doesn't change the energy. Okay, what direction would a magnetic field have to point for a beam of electrons moving to the right, go undeflected to a region where the electric field is vertically pointing upward? Right. Let me give you a little background here. We have this electrons, they're traveling in this direction. There's an electric field pointing upward. So the first question you want to ask yourself is, what is the direction of the force due to the electric field on these negatively charged particles? Is it up or is it down? And then I want to ask myself, the question is, how can I have a magnetic field that will cause these particles to move without being deflected? So the first question you want to ask yourself is, what is the direction of the force due to the electric field on these negative particles? And then you'll need to have another force that's opposite the electric field that causes these electrons to move through undeflected. And then what is that magnetic field that causes that magnetic force? We have two forces here, the electric force and the magnetic force. Ask your neighbor if you're not sure what the answer is. Okay, I'm gonna stop at 150. 150. Do y'all have the answers to these somewhere, or do you just know how to do them? You just know how to do them? Like, did I post the answers or anything? No. Okay, good. I'm gonna stop. It's just many of you have gotten this, so D is right. That's awesome. Let me show you how the answer goes. So, not that you need to know because you already know. The electric force is down. And the electric force for a negatively charged particle is opposite the direction of the electric field. And so that means in order for this to go through undeflected, my magnetic force has to be up. Hey, y'all remember those big TVs and the big wooden cabinets? They were like as wide as they were deep. Those cathode ray tubes. Those work by this principle. They have an electric field and they have a magnetic field, and they modulate that electric and magnetic field to cause your electrons to scan across the CRT, the cathode ray tube, and create light on your screen with a TV. I mean, modern TVs don't work that way, but the old TVs that you had to bang on the top to make them work, do y'all have one of those? Your grandma had one? We still have one at home. No, we don't really, but it hasn't been that long that we have one. Okay, so now I want to know what is the direction of the magnetic field that will cause this force. So you let your fingers go in the direction of B. Your thumb goes up, and so your magnetic field should be out of your palm, which would be into the page, right? But they're negative particles, so it's going to be opposite that. It's going to be D. So there's lots of thought that has to go into this question. What is the direction of the electric force? For negative particles, it's opposite the direction of the electric field. Then our magnetic force has to be opposite that. Then the magnetic field that causes this force is going to be into the page, except these are negative particles, so the magnetic field is opposite direction out of the page. So D is the right answer. That's what y'all are thinking when you put D? Yeah. Awesome. Okay, good. A horizontal wire carries a current. What is the direction of the force on the wire? Let me try to fill in this. It's a little... Oh, you can... Y'all see that in the back? Ashley, you can see this? Okay. Yeah. All right, what is the direction of the force on this wire? All right, I'm going to stop at 48. Okay, awesome. E is right. It's out of the page. Remember, we have two applications of the right-hand rule. This is the second one. I is in this direction, B is in this direction, so it's going to be out of the page. You'll have several questions regarding the right-hand rule on your test, and we'll work through some others that are similar. So it's out of the page. This one, I is up, B is up. What is the direction of the force of the wire? Stop at 25. Awesome, C is right. Remember, our force is I LB sine theta. And if theta is equal to 0, as it is here, the sine of 0 is 0. So it is 0, C. Let's see, I tried this one, but I botched it the other day. What word can you make shorter by adding two letters? You say, I don't know what. Short. Yeah, you may add two letters. You add ER to short, and it makes it shorter. Okay, a rectangular current loop is in a uniform magnetic field. What is the direction of the net force on the loop? Remember what net force is. What is the direction of the net force on this loop? All right, I'm going to stop at 45. Okay, good. C is right. It doesn't really matter what the direction of the forces are. The only thing that matters really is that I know that the force on this wire is in one direction. The force on this wire is in the opposite direction because the currents are going in opposite directions, and so they have opposite forces. So the net force on this entire loop is 0 because you have equal and opposite forces for each of the wires, each of the 4 wires. Okay, and this one you do need to know the actual direction of the forces. We've seen a question like this before, but remember that this loop is rotating on an axis. And so if I have a current in the loop as it's shown, it's going into the page here, out of the page here. What is the direction that it will turn? Remember, our magnetic fields start in the north and end in the south pole of a magnet. Hey guys. All right, I'll stop at 1 minute. 1 minute. Okay, awesome. C is right. I find the force on each one, recognizing that my magnetic field is in this direction. So for example, taking this side, my force is down, Over here, my force is up, so it's going to rotate clockwise. Rotate clockwise like that. Okay, this is using that third application of the right-hand rule. If I have a wire, the magnetic field rotates around, if I have a wire with a current going in this direction, the magnetic field goes around in this direction. Let my thumb go in the direction of the current, and my fingers wrap around like this. So here I have two wires, one's going into the page and one's coming out of the page. What is the direction of the magnetic field at point P? Is it A, B, C, or D, or is it 0? So you'll want to draw your two vectors for each of the magnetic fields due to those wires, and then figure out what is the vector sum of those two vectors. I'll stop at 45. I'm sorry. When 45 students answered, that's when I will stop. I will stop at 1:15. Okay, good. C is right. For this particle right here, or this wire, my magnetic field at this point is in that direction. The wire's coming out of the page, and so my magnetic field goes around in this direction. So at this point, it's tangent to that circle. It's going to be in that direction. Now, due to this wire, it's into the page. My magnetic field will be in this direction. So if I add up those two vectors, they're going to add up to give me the vector C. They will also have x and y, x components, but those two x components will cancel out. And I'll just have the vector C. That's just showing you those vectors. Okay, let's try this. Here I have 4 configurations of wires. In which case is the magnetic field at the center of the square the greatest? ABC, or is it the same for all? So you're doing the same process, but you have a lot more wires to deal with. If you look back at old tests, you'll sometimes see questions like this, but they sort of take a long time, so you're probably not going to see one like this on the test. Maybe one more like the previous one to just sort of test your knowledge of that, but not with such tedium as this one. But let's try it anyway for practice. All right, about 10 more seconds. I'll stop at 1:05. Okay, good. I think that is right. Let's take a look and see. So we want to go through each one. So starting here, starting with this wire, the magnetic field is in this direction. For this wire, the magnetic field is in this direction. For this wire right here, it is in this direction. And due to this wire right here, it's in this direction. So the magnetic field due to this first configuration is 0. It just goes away. And then if we do it for the second one, which you all said was the right answer, I think you're right. Due to this wire, it's going to be in that direction. Due to this wire, in that direction. Due to this wire right here, the magnetic field is in that direction. And then finally, this wire right here, the magnetic field is in that direction. So you see you get a different configuration of vectors for this one that has a larger magnitude. And then that last one, I'm pretty sure is also 0. Is that right? I'll confirm that. Yeah. All right. Good. So that's the right answer here. You're doing pretty good on this. Students usually don't do this well on these quizzes. Okay, just a few more. Positive charge moves parallel to a wire. If a current is suddenly turned on, what direction will the force act? So a couple different things you want to think about here. This wire will generate an electric field, or excuse me, a magnetic field, and this particle then will be moving in that magnetic field. What is that particle going to do when you turn on that wire? All right, just about 10 more seconds. I'll just stop at 1 minute. I'll stop at 105. Okay, good. C is right. So if I turn on this current, I get a magnetic field that is into the page over here and out of the page over here. Into the page, out of the page, into the page, out of the page. And now I have this velocity vector moving through this magnetic field vector. V is up, V is out of the page, and so it's going to then experience a force that is in this direction. So that was C, is that right? Yeah, C is right. Alrighty, now you could very easily calculate the force that this particle feels, because I know that the magnetic field here is that mu naught I over 2 pi r. So at a distance r from that wire, I have this magnetic field, and then the force on this wire is just going to be the charge times the speed times the magnetic field. It's perpendicular here, so this was in the screencast, so make sure that you're aware of how this works. But the magnetic field due to a current carrying wire is just mu naught I divided by 2 pi times the distance from that wire. And then finally, 2 straight wires, or almost finally, a couple more questions. 2 straight wires run parallel to each other, each carrying a current in this direction shown. 2 wires experience a force in which direction? Each wire generates its own magnetic field, and then the other wire is operating in that magnetic field. So a couple different things you'll need to do here. All right, I'm going to stop at 55 seconds. 55. Okay, good. A is right. Imagine the one on the right. It generates a magnetic field that is into the page, out of the page, into the page, out of the page, into the page, out of the page, like that. And then this wire, then the green wire, is sitting inside the magnetic field generated by the blue wire. And so I have a current in this direction, a magnetic field that's out of the page. And so those 2 wires are both going to experience a force that is equal but opposite. So the green wire will experience a force in this direction. And likewise, if you go through the steps, you'll find that the blue wire experiences a force in that direction. Those 2 forces are an action-reaction pair, like we saw in Newton's third law, so they're going to be equal but opposite. In the screencast, we went through and sort of derived what those forces are. So that's on your equation sheet, but just know how to find that. And then one more. What is the direction of the magnetic field at the center of a square loop of current, like this? done, we're going to, oh, you have your test. Okay. All right, I will stop at 40 seconds. 40? Very good. E is right. This works very similarly to that third application of the right-hand rule. Let your thumb go in the direction of the current, and then it folds around. It gives you the direction of the magnetic field. So for example here, my magnetic field is into the page, out of the page. Likewise, into the page, out of the page, into the page, all around this. And so at point P, it's going to be out of the page. E is right. Okay? Good luck on your test. All right. We'll have a couple more questions from the notes. Any questions, though? I realize it's sort of strange doing it this way. Okay. All right, let's had a couple more things. Where was it? Right here, I think. Yeah, we'll do this one. We're going to skip the next one, but let's do this one. The point A is equidistant between these two long parallel wires. What is the direction of the magnetic field at point A due to these two wires? So each of these wires makes its own magnetic field. At this point, what is the sum, the vector sum of that magnetic field? Remembering that a magnetic field is a vector. All right, I'll stop at 105. 105. Very good. B is right. It's going to be out of the page. B. Due to the one on the right, I have into the page, out of the page. Over here, the one on the left, into the page, out of the page. So at point A, it's going to be out of the page. Now, if we had a situation where instead it was going in this direction, I would have my magnetic field would be switched. And so at this point, I would have no magnetic field at all. No magnetic field. Because the two magnetic fields would cancel themselves out. That vector, the vector sum would be 0. And also, make a point that this would only be the case at the very center. Because at the very center, the magnetic field are equidistant from this wire, and I'm equidistant from this wire. And so the magnetic fields would be equal but opposite.
So for that one, if it was more towards the left, then it would be into the page.
Right. If I was more over in this area over here, it would be into the page. And likewise, over in this area, I would be out of the page. Yeah. All right, we're going to skip this other one. And I think that's it for this chapter, if I'm right. Listen, I don't like doing this like where we don't cover it in class, but make sure that you know about the solenoid and stuff like that. We're going to move on to the next chapter. But are there any questions right now about chapter 5? Y'all go back and take a look at it. If you haven't watched those screencasts, go back and take a look at it. And you can shoot me an email and just say, look, I'm really not getting this. So, and then I can spend a little more class time on it. But like I said, missing last week, or whatever day. What is today? It's Monday, missing Friday. Oh my God, I don't know about y'all. Yeah. But anyway, missing Friday is sort of through our king and some things. But let's move on to chapter 7, or 6 rather. And then if you have questions as you're going through the screencast for the remainder of chapter 5, just shoot me an email and say, I just don't understand, blah, and we can spend a few more minutes on it in class. Or you can come by my office too if you want to do that. Did y'all see the British guy with the solenoid? The video on the video? See, y'all, you're missing out. Okay. All right, let's look at reflection and refraction. So we're moving sort of into the last home stretch for this semester, and then no more physics, sorry, for many of you, all of you probably. And it's a section on light. Actually, at the very end, we'll do a section on sound, which is going to be similar. But this is the section on light, so this chapter and the next chapter and the following chapter all sort of fall together. This first chapter is fairly short. It's on reflection and refraction. You've probably seen this before in physical science, maybe, how mirrors reflect, how different media refract light or bend light. And so we'll look at that. It's a bit different than what we've been doing. There's no right-hand rule. There's no circuits. There's none of that. Most of the math is pretty straightforward. But we'll look at sort of how light goes and propagates through different media. And that can be quite interesting and actually quite applicable for what many of you will do because, you know, might use microscopes or other instruments, optical instruments, are often commonly used in scientific fields. So let's look at reflection and refraction. First of all, I just want you to have a sort of basic understanding on the history of the nature of light. In the 17th century, Newton developed a particle theory of light. He believed that light was a particle, and he described light very much as a particle. He treated light like a stream of particles. I think he called them corpuscles, if I'm not mistaken. I forget exactly. But he treated them like a stream of particles. So if you had a flashlight or a lantern or whatever, and it was shining light, he would say that we have individual particles that are shining onto a surface, and he treated light very much like a particle. And the reason that he did that, he had a good reason, because light always demonstrated reflection. And reflection is purely a particle quality. Or you ever play pool, or you play tennis, or any kind of sport where you have a ball, then you know that when you bounce a ball off of a surface, if I bounce a ball off of a surface, that the incident angle is equal to the refracted angle, reflected angle rather, that theta I is equal to theta R. And that's purely a property of particles. And so Newton observed this, that light reflected the way particles do, and he said, aha, light must be a particle. Huygens, on the other hand, you probably never heard of Huygens. He wasn't quite as famous as Newton. And that's part of the reason that his idea was sort of squashed at the time. But he was a contemporary of Newton, and he said that light was a wave. So he developed a wave theory of light. And so he treated light like a wave. And so if he thought of a flashlight, of course they didn't have flashlights, but if he thought of a lantern and the light was coming out of it, then he thought of the light coming out as a wave, like waves on a lake, or, you know, like sound waves. The reason that he thought this is because light demonstrated refraction. And we'll learn about what refraction is. You probably know what refraction is in short, but refraction can just be referred to as a slowing of light when it enters a medium, or more commonly, it's when light actually changes direction. So if you look closely at waves like out on a lake, as waves are traveling across a lake, if they enter a place where the lake changes, like where it becomes shallower or enters some sort of obstacle, they'll actually bend. And so refraction is very much a wave property. Huygens knew this, Newton knew this, and they also saw that light refracted in the same way that waves did, and so they said that light is a wave. Now, Huygens' idea wasn't accepted for a couple of reasons. First of all, waves need a medium to travel. So they understood that sound, for example, if you were to suck all the air out of this room, that the sound wouldn't travel through this room because it needs a medium. That's why you don't have sound in space. You don't have waves that travel without any kind of medium. So waves always need a medium to travel. And then the second thing is that waves could bend around obstacles. But light could not. Or at least they thought that it could not, or so they thought. But we'll see that that's not true, that light can also bend around obstacles. We'll see that in chapter 8, they thought. And this is pretty easy, that way to see, or rather to not see, right? That you guys can hear me right now, can you? But you can't see me. So the waves are bending around this obstacle, but the light is not. So you can't see me, but you can hear me. Of course, they didn't have modern PA systems and stuff, so just ignore that. But the waves can bend around obstacles, but light could not bend around obstacles, or so they thought. And we'll see that that's not really true when we get into chapter 8. All right. It's at 11:40. We have so in 19th century. Y'all have a good day, okay? See you Wednesday. Unfortunately, I'm gonna have to let you out a little early on Wednesday, so like 10 minutes probably.